Okay, thank you for coming back. I know many of you are already not here because you're traveling, so that's not a problem. This is sort of the tradition of our school and also this time of the year. So don't feel unhappy, okay? And don't feel sad if you're not here, okay? So I totally understand that. What we want to do today is, of course, not to teach anything new, right? Because you guys are traveling and also having some wonderful family time. So what I want to do is to talk about the last homework, just to go through some of the questions as a way to review the things that we have been learning so far, and then maybe answer some questions, things that you curious about knowing, could be inside this course or outside this course, so just make it a good time to have a conversation. So that's the point. Okay, so to start with, I want to share with you this homework assignment. This is homework number 8. The last homework assignment that will be due the Friday after the Thanksgiving, so that will be the 2nd of December. The 2nd of December. We are not able to collect homework because there's a new rule from the Provost's office that starting from this year, no homework project should be collected during the week before the final exam. So if you see any professor who's going to collect homework and project, you can say, hey, have you looked at the new policy? Okay, so now homework number 8 will contain how many questions? 7 questions. But I'm going to pretty much go through every question with you today and then the week after we come back from the Thanksgiving. So I want to make sure that you really understand how to do things. Okay, so let's look at this problem. The first 3 problems, they are all within our capability. So they are from the chapter 6. About law of large number and central limit theorem. So I want to use these problems as a way to demonstrate how to solve the problems using these theorems. So let's look at the first one. The first one says this. Consider an experiment of drawing n Poisson random variables, x1 through xn, where small n, they are all Poisson with a parameter 1. Okay? And I'm going to define y to be a binary random variable. You have a state of 1 or 0. It is 1 when your x is bigger than or equals to 1, and it is 0 when xn is 0. Then I'm going to construct a sample average called the ym bar. I want to use Python and MATLAB to generate a plot looks like this. You remember this plot? This is a plot that we showed in the lecture. Okay, we want to make a plot like this. And so what you are expected to do is to have x-axis with 10 to the power 2, 10 to the power 3, 4, and 5. Y-axis you have the probability values. You have many crosses, so they represent the samples. And then you have the red line. So those would be the 1 standard deviation or 3 standard deviation, forget which one it is, but you'll find the envelope to bound these numbers. And the point here is that I want you to have a feeling of this random variable ym bar. Okay? Ym bar is a random variable, and therefore it has its own PDF. The PDF can be seen by looking at the density of the crosses in this plot. So if you recall our discussion of the law of large number, we mentioned that this is the number of samples n, and then you're going to construct this sample average called yn. If your n is 100 samples, then you should imagine that all the crosses, they may be located here and there. But if you are going to 10 to the power 5, then all the crosses, they should be located in the center. So there should be some convergence of the distribution. And therefore, if you can see this, if this is really a Gaussian, then the mean wouldn't change. the mean will still be in the center, but then the standard deviation should change. This is what we are asking you to plot in this diagram. Okay, so going back to this exercise, we are not looking at a Gaussian, and we are also not looking at Bernoulli, but we are looking at a Poisson. Right? We're looking at a Poisson. So each xn is a Poisson of 1. And then I'm going to define yn. It will be either 1 or 0 if xn is bigger than or equals to 1, and xn is 0. Okay, xn, the smallest value of xn will be 0. Hold on, this is so big. Okay, so the smallest value of xn is 0, because Poisson is, it is an integer. So what can we do here? Well, we want to draw the samples of yn, right? We want to draw the samples of yn. One naive way, right? One extremely naive way is to first generate all these Poisson counts. Okay, so you start with Poisson 1. You draw the xn, and then you construct this yn. Okay, and then you construct this yn. You basically do a truncation. Then you construct this yn bar, which is 1 over n, and n going from 1 to capital N of yn. Okay, so there will be multiple process. You start with Poisson, and then you draw n of these Poissons with the truncation. You form this average. You construct this yn bar. You get yn bar n. Okay. Now the problem is that if you do this, step 1, step 2, step 3, you can only get 1 point. You can only get 1 point in this plot. And how many points do you need to generate? You have not many, maybe a million of these points. So if you really go through this naive process, it's going to take you forever to generate this plot. So what you can do here is that you can think a little bit carefully of is there any trick that we can employ to make it plot faster? By the way, there's nothing wrong. If your distribution is very complicated, this is the only way to go through it. Right? You just draw xn, yn, draw this sum, form this yn bar, and so on. And remember, there's a trick that we used before is that you can generate a big array, n trials, and then big N, form an array instead of forming each individual samples, and then you write a double for loop, so that will take more time. But the trick I want to introduce is the following. Your xn is Poisson of 1, right? And then yn is binary. Yn is binary when xn is bigger than or equals to 1, when xn is 0. So I ask, what is the distribution of yn? Well, yn is not a Poisson. Yn is only binary. So there are only 2 states for yn. Probability that yn equals to 1 and probability that yn equals to 0. What is the probability that yn equals to 1? What is the probability that yn equals to 0? Well, the probability that yn equals to 0 is the probability that your xn is 0. Now, what is the probability that xn is 0? Since this is Poisson, we know that it is going to be lambda to the power k e minus lambda divided by k factorial, right? So this is the Poisson formula. What is the lambda? Lambda is 1. Okay, so this is Poisson of lambda. So now I have Poisson of 1, so lambda is 1. What is k? K is my state, and my state is 0. So just put a 0 here, times e to the power minus 1 divided by 0 factorial. I'm just evaluating this Poisson distribution. at the state of 0. And so you take this calculation, 1 to the power 0, this is 1, 0 factorial, this is 1, and so you have e minus 1. Pretty easy, right? Now, how about yn? Yn is equal to the state of 1, and that's just the complement of yn equals to 0. So you have 1 minus the probability of yn equals to 0, and so this is 1 minus e minus 1. Right? So you get the probability mass function for yn. I have already converted the distribution from xn to the yn. If you do it on computer, you draw all the xn's and then you do this truncation. You look at the probability is going to follow these two numbers. Okay, so I'm just skipping this calculation from computer by using the paper pencil. So once you have that, then I ask, what is the distribution for yn bar? What is the distribution for yn bar? Yn bar is 1 over n going from 1 to capital N of small n. Okay? And if the individual y small n's, they are two-state, which is a Bernoulli random variable. I am summing in Bernoulli random variable, then what is the sum? There's a name. Binomial. Excellent, right? So this is binomial. And so we know that this is going to be binomial, right? Binomial, what would be the average? The average of this binomial, now let me remind you what is this binomial. So if yn is Bernoulli of P, then sum of yn will be binomial n times P, and then the variance will be n times P times 1 minus P. Okay, so this is the variance, and also the mean. There will be a binomial distribution. And so now if I put a 1 over n here, then 1 over n times this sum, it will become a binomial. It's no longer just np, it will become p because you have a 1 over n in front of it, right? Because if you take the expectation of 1 over n sum of yn and going from 1 to capital N, this is going to be 1 over n, the expectation of the sum, and so that will give you 1 over n times np, so you get p, right? So you have p here. What will be the variance? Well, the variance of 1 over n, yn, that will give you 1 over n squared, and then you have the variance of yn, you sum everyone up. And so you have a p times 1 minus p, and then you have n at the denominator. So you have p times 1 minus p divided by n. Now this p times 1 minus p is just the variance of a Bernoulli. Bernoulli, you know the variance is p times 1 minus p. Okay, so you know that this is, if I start with a Bernoulli, you go to binomial with these two parameters, then let's go back to this problem here. Now I have this Bernoulli, and then I take the sample average, so it would be p here. Now what is the p? P would just be this, 1 minus e minus 1. This is my p. Right? So this is the probability getting 1, so this is my p. And then the variance would be e minus 1 times 1 minus e minus 1 divided by n. So this is my variance. So just map this p to this number, 1 minus p to that number, and then you have 1, you have n. So what does it mean? Well, in order to plot this diagram here, I don't have to go through the x and then to y and then to yn bar. I can just go directly to MATLAB or Python, call the binomial random variable by specifying the n and also the p. The p will just be this number. Just call this number, then you can draw a point right there. Okay? you can plot the point right there. So if you go to the textbook, of course, the solution is down here. No, I'm not going to show you. You can actually just call binomial random variable, and then specify the n, specify the p. You can start to plot all these points. Of course, you need to loop through it. You need to loop through multiple times to loop through all these samples in this plot. You get a point? Good. Okay, so this is exercise 1. It is a very good visualization for you to understand what is going on in this law of large number. The law of large number really says that as n goes to infinity, this yn bar will converge to a number, which is the population mean. So that is a very useful result. Any questions so far? Good. Okay, so that's exercise number 1. Now let's talk about exercise number 2. Let me zoom in. So this is again this is central limit theorem. Okay, so it is a very good demonstration of the central limit theorem. Oh, your laptop is dark. Okay, cool. Okay, so exercise number 2 says this. You have a sequence of random variables, their ID, and then they have the mean individually. They have a mean of mu. They have a variance of sigma square. And then I am going to assume that the xn can be any distribution. It doesn't need to be Gaussian. Although I mentioned that they have a mu, they have a sigma square, but they don't have to be Gaussian. They can be any distribution with a finite mean and finite variance. So we don't know what it is. And then I'm going to construct the sample average called xn bar. Okay, I'm going to construct the sample average. I want to know the probability. Now, clearly, when you encounter this problem, the first reaction, if I don't tell you what central limit theorem is, you will be like, I don't even know what the distribution is. How can I do the integration, right? I don't even know what distribution to use. So how can I possibly even calculate this probability? Central limit theorem says that if you want to calculate this probability, because your n is big enough, you can approximate it by the Gaussian. So let's work on the details. How do we tackle this problem? So this is a very good demonstration if you are not following the proof that we did last Friday, which is okay, but then when you sit down and apply this theorem, then this will be useful demonstration. So let's work on this problem A. You want to look at the probability that your xn bar is bigger than 2 mu. Okay, xn bar is bigger than 2 mu. Now, let's draw the picture. So here you have some unknown distribution. So this is your f of xn, each individual xn. You have a crazy distribution, which I don't know what it is, but I know there's a mean, there's a variance. As I am forming the xn bar, I can look at the PDF of this Sm bar. Okay, xn bar is a random variable, and therefore xn bar has a distribution. It turns out that as n becomes big, it will be more or less look like this. More or less, okay? The shape is a Gaussian. And then I ask, where's the center? Well, the center would be the mu, right? Why? Because if xn bar is 1 over n sum of xn n going from 1 to capital N, then the expected value of xn bar will still be mu, right? Because each individual random variable has a mean of mu, the ID, and therefore when you form the sample average, it will still be mu. So I know that it is mu. And then what I'm asking is that I'm asking, what is the probability that my random variable is bigger than 2 mu? Now, where's mu? Mu is here. Then 2 mu is here. Oh, sorry. So 2 mu is here. right? So this is mu, this is 2 mu. I ask, what is the probability that my xn bar is bigger than 2 mu? I'm asking this area, which I think I can calculate that. So how do we do this? Well, clearly on the left-hand side, you can't do anything. You don't know the distribution. You need to take the sum, and convolution, and so on. It's very hard. But on the right-hand side, I can approximate it. So the probability that my xn bar bigger than 2 mu is what? Well, let's look at the diagram. It has to be Gaussian, right? It has to be Gaussian. It has to be the Gaussian, some Gaussian, okay, dx. I have to integrate from 2 mu to infinity. So that's the approach, right? Gaussian integrating from 2 mu to infinity. So that would return me the probability. But then I need to ask, what is that Gaussian? Gaussian of what? Well, Gaussian, you should have a mean and you should have a variance. What is the mean and what is the variance? So the central limit theorem tells us that the mean of this Gaussian has to be the population mean, right? Because you form the xn, I ask, hey, what would be the mean? Well, the mean of this xn bar, which is expected value of xn bar, this is mu. Is something I know. Then I ask, what is the variance? The variance of xn bar will be, well, I know this is sigma squared over n. Because each individual random variable has a variance of sigma squared, and therefore, if you take the sample average, then the variance will become sigma squared divided by n. You can do the calculation. And so, this thing here, xn bar, has to converge. I put a snake arrow just to denote that it's converging in some way to this Gaussian of mu n sigma squared divided by n. Okay, mu and sigma squared divided by n. So let's go back to here. Now I want to do this integration from 2 mu to infinity for this Gaussian. This Gaussian will be mu n sigma squared divided by n. This is my Gaussian. So let's do the calculation. So I want to integrate this probability of xn bar bigger than 2 mu. This is the integration from 2 mu to infinity of a Gaussian mu sigma squared divided by n, and then there's a dx. We understand what the symbol means, right? Put a 1 over the square root of 2 pi sigma squared divided by n times exponential blah, 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 any chain of things. Right? Just put it in. So you have this integral. Okay, so how do we calculate that? So do not panic. This is going to be the same as you look at this diagram, right? So you look at this diagram, you know you're integrating from 2 mu to infinity. This is the same as you take 1 minus the integration from minus infinity to 2 mu of this Gaussian, and then dx. Okay, so from minus infinity to 2 mu, this is the complement. And there is a notation. There's a notation, if you recall, where we define this concept called the standard Gaussian, or the Gaussian with a zero mean unit variance. We have that symbol. That's called a phi function. Okay. So the phi function, now if you forget, that phi function says this, okay? So the phi function, if you integrate, right, a to b, this Gaussian something, dx, it can be written as the phi function evaluated at b minus mu divided by sigma minus phi of a minus mu divided by sigma. Remember that? So the standard Gaussian, you evaluate the upper limit minus the mean divided by the standard deviation, and then you subtract the lower limit, do the same thing. Okay, so this is the standard Gaussian. So let's go back to here. Here the thing will be a 2 mu minus your true mean divided by your standard deviation, which will be sigma divided by square root of n. Okay, why is it sigma divided by square root of n? Because your variance is sigma squared divided by n, and so your standard deviation is sigma divided by square root of n, which comes to here. Your mean is here, and then your upper limit goes to here. So you have the upper limit minus the mean divided by the standard deviation. You get this formula. The lower limit you don't need to worry because the lower limit is at minus infinity, so that's going to give you 0. Okay, so this is going to be the result. You have this 1 minus the phi function, and let's just do some simplification. You will have phi of mu divided by sigma over n. Good. So if you make your n bigger and bigger, what will happen is that your Gaussian will become narrower and narrower, so eventually become a delta function. Then this probability will become 0, and should make the n bigger and bigger. Right? So this is the answer for this part. If I want to calculate this probability here, originally I have no way of calculating this probability because I don't even have formula for the PDF. However, because I am calculating the sample average, and therefore I can use the central limit theorem to do this approximation. I can use the Gaussian PDF to calculate the integral. This is how I come up with this result. You have 1 minus the phi of this chain of things. Is it okay? Okay. Now, if this is okay, let's move on and talk about something even harder. Do I have blank papers? Okay, I do have blank papers. Okay, so let's look at part B. Part B says I want to look at the probability of mu minus sigma between less than or equals to, it can be equals to bar of xn and then mu plus sigma. So let's again look at the picture. The picture here is that you have a Gaussian, centered and mean. And now you are looking at the probability that you are mu plus sigma. Mu is in the center. Mu plus sigma, it will be here. This is mu plus sigma. And then mu minus sigma, it will be here. Mu minus sigma. So eventually you're trying to calculate this probability in the middle. So without doing any calculation, let me ask you, what will happen if my n becomes big? My n becomes big, right? So when n becomes big, your Gaussian will become more concentrated in the middle. So you should expect this probability to go to 1, okay? You have more concentration in the middle. So n large, the same diagram will become something like this. So you still have this mu minus sigma, mu plus sigma. This is mu. Now, your sigma is not changing. Your sigma is given by the problem. Sigma is the variance of each xn. This is sigma. You take the variance, the sigma square. If you are talking about the variance of xn bar, then this is sigma squared divided by n. Okay? So only the variance of xn bar will shrink. Your original variance for xn wouldn't change. So this is still the sigma. This is still the sigma. So as n becomes large, you should expect the probability to become 1. And let's see if this is true. So let's look at this calculation. You want to calculate probability that mu minus sigma xn bar less mu plus sigma. So this is going to be what? This is going to be, I know the Gaussian distribution, right? So this is Gaussian of mu and sigma squared divided by n. By central limit theorem, I know that the distribution is going to look like this. Then this probability can be approximated by the phi function, evaluated by the upper limit. The upper limit is mu plus sigma, minus mean, divided by the standard deviation. Mean and standard deviation, minus the lower limit, it will be the phi evaluated at the lower limit minus mu, this is the mean, divided by the standard deviation. Okay, so then let's do some simplification. The simplification will give us phi, you have sigma divided by sigma over root n minus phi, and then you have minus sigma root n. So that will give me phi of square root n minus phi of minus square root n. This is my result. Now, as n goes to infinity, then this probability will give you what? You have the standard Gaussian, you evaluate at the infinity, this is going to become 1. Okay? So this probability thing here is going to become 1, because this is going to 1, this is going to 0. So 1 minus 0, you get 1. So this is consistent with what we were talking about, that as your n becomes big, your Gaussian will be concentrated at the mean. So part C will just be similar. Just replace the formula by, instead of sigma here, it will be sigma divided by square root of n. So you can do some calculation and see what will happen. Okay, so part C will be straightforward. But I think this exercise number 2, illustrates how do we use the central limit theorem to do the approximation. Right? Again, I want to emphasize that in many situations you don't have access to the actual probability distribution, but since you're talking about sample average, you can approximate it by central limit. Very useful result. Okay. Any questions? Is it clear? Okay, looks good. So this is problem number 2. Let's look at problem number 3. Okay, problem number 3 is about the is try to ask you to derive a little bit, just a little bit, really a little bit of the law of large number. So the law of large number that we have seen, if you recall, the way we prove it is that we want to prove that the probability that your xn minus the mean bigger than the epsilon, we show that it is going to be less than or equals to the variance of your x individual n, and then there's an n, there's an epsilon square. So this is called the Chebyshev inequality. And then we say that the limit n going to infinity of this probability thing, it is going to be 0. And therefore we claim that the Chebyshev inequality, as the n goes to infinity, you're going to get the convergence to 0. And this convergence is a sequence of numbers between 0 and 1. It is going to converge to 0. So that's the Chebyshev inequality. It's easy to prove. Now, in this problem, we are going to break one of the assumptions that we made in the Chebyshev inequality, which is the assumption that all the random variables x small n's, they're independent. We're going to introduce some dependency, but this dependency is really small. Very mild dependency, according to this equation here. You assume that that there's a covariance between xi and xj. Okay. Now, if covariance of xi xj is 0, then they're independent. If they're independent, it implies that. But I'm going to assume that there's some dependency given by this covariance structure. The covariance structure says that xi and xj, if I equals to j, then you get sigma square. Okay, so if they are the same, then you get the variance back, so which is true. 0 otherwise, but there's a middle case. The middle case is this: there's a rho times sigma square when I minus j is 1. Okay, so what it means is that you draw a grid of points. They're equally spaced. Let's say you are I here, and then you are j here. If they're 1 point apart, then there will be some correlation. But if your j is 2 points apart, there's no correlation. So this is what we mean by a short-range correlation, which is true in many of these engineering problems. Short-range correlation, you only have one step. The guy next to you has a correlation to you. The two persons away from you have no more correlation. Okay? You can extend this concept to 3 or 4 people, but 2 will be the easiest, right? So your neighbor will have some correlation. So in this case, we ask, is it still true to have this Chebyshev inequality? Right? So this is what we want to prove. Okay. So what we want to do is that we want to compute 2 things. Let's see. So according to the problem, we want to compute the mean and the variance of the sum. Eventually, we want to compute the mean and variance for the average. Okay. So let's start with the sum. So the sum Sn is x1 plus dot 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 plus xn. I want to find the mean. Expect the value of Sn. And then I want to find the variance of Sn. I want to find that. Once I can find these, then of course I can tell you the expected value of xn bar. I can find you the variance of xn bar. Focus. Oh, okay, so now this is focused. So you have expected value and the variance, then you can plug into the Chebyshev inequality and then prove things. Okay, so now let's find the sum. The sum Sn. Sn is just the sum of x1 plus dot 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 plus xn. And now I know that they have a common mean. What is the mean? Well, I don't know the mean. Okay, so I would just say that expected value of xn, small n, is mu. And so now I have a sequence of random variables. They are dependent. They're dependent. But it doesn't matter. The expected value, if you recall, the expectation itself is a linear operator. Because this expectation is just integration, right? So expected value of a random variable, another random variable, even if they are dependent, it doesn't matter because you are going to take the integration of x plus y, right? And then you have fxy. So it doesn't really matter how many of those you have, dx and dy. It doesn't matter, okay? You can always have expected value of x1 plus expected value of x2 plus dot 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 plus expected value of xn. That is always true, regardless if it is dependent or not. So you have this, then let me get another paper. So if you have this, then you can show that the expected value of Sn, it will just be expected value of x1 plus expected value of x2 plus dot 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 plus expected value of x capital N. That's going to give you a mu, a mu, a mu. So here you will get n times mu. So the variance, so the mean is easy to calculate. Okay, so now how about the variance? The variance would be slightly more trickier. So let me make sure that I know how to do it. So the variance of Sn. So the variance of Sn is what? It would be the expectation of the summation of xn minus mu square and the n going from 1 to capital N. I think, oh, it's not even like that. Okay, so I need to do this more complicated thing. It would be expected value of this, because there's a correlation going on between the different random variables, and so you will have x1 minus mu square times x2 minus mu square plus dot 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 plus xn minus mu square. Don't stop here yet. You still have x1 minus mu times x2 minus mu plus x1 minus mu, x3 minus mu, plus dot, dot, dot is a big chain of numbers, okay? This is what we call the correlation, right? So if you recall the covariance of a random variable, you need to think about all the cross terms. The good news is this. Because you only assume a short-range correlation, anything that is bigger than 2 points apart, you can remove them. Okay, so let me show you what's going on here. You have this big expectation, if you want me to write it, it will be a huge array, okay? It will be x1 minus mu square, and then here it will be x2 minus mu square, and then you have xn minus mu square, and you need to add everyone up, right? Because according to this formula, there are so many terms, you need to add them up. But if I arrange them in this way, x1 minus mu times x2 minus mu, and then x1 minus mu, and then x3 minus mu, and so on, okay? You can see that there are terms that you can cancel out. This one doesn't really matter because I only have a short-range correlation. Anything that is bigger than one neighborhood apart, they don't have any correlation. See that? Okay? So this is gone, this is gone, this is gone. So basically this entire lower triangle, you can ignore them. The only thing that will be remaining will be all the diagonal terms and also this chunk of elements. See that? So here. This band will be here and also the diagonal will be there. And what we need to do is to write down how many of them are there. So you look at this equation here. What would be the expectation for these guys? They are just sigma square. Okay? And what would be the off-diagonal terms? They would just be rho times the sigma square. So let me see if I have, these are all written. Do I still have papers? Okay, so what I have left is this expected value, a big array of numbers. I need to sum everyone up in this array. And then I have sigma square, dot, 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 until the last one is sigma square. And then I have rho, sigma square, and so I have rho, sigma square. And then I have rho, sigma square, and so the last one will be rho, sigma square. And then the rest will just be 0. I need to sum everyone up in this array. So I ask, hey, what is the final value here? So the final value would be, this thing will just be n times your sigma square, okay, plus rho times sigma square, and how many of them are there? Well, this will be n minus 1, and you have 2 times. Do you guys follow? Okay. Along the diagonal, you have n of the sigma square. Along the off diagonals, the upper triangle, you have rho sigma square, but you have n minus 1 of them. And then you have the lower half, you have another n minus 1 of them. So you have n times this plus 2 times n minus 1 of that. So this is the variance. This is the variance of Sn. Okay, so let's recap what we have shown. We have shown that the expectation of Sn is n times mu. We have shown that the variance of Sn is n times sigma square plus 2 of n minus 1 rho sigma square. We showed this. Therefore, I can show that the expected value of xn bar, which is the sample average, it will just be expected value of Sn divided by n. So that will give me mu. And then I have the variance of xn bar. That will give me 1 over n squared times the variance of Sn. So that will give me sigma squared divided by n plus 2 times of 1 minus 1 over n times rho sigma square. Am I right? Oh, I have 1 over n and n square. I have this. So that sort of answered the question of part A, how to find the mean and variance of Sn, and from there, we can actually prove the weak law of large number using the Chebyshev inequality. Because the Chebyshev inequality says this, expect a probability of xn minus mu, I want to calculate this, right? And I know that it is going to be less than or equals to the variance of xm bar divided by epsilon squared. Now there's no n because I'm putting a bar here. And so this is going to be sigma square divided by n plus 2 times 1 over n minus 1 over n square times rho sigma square, and then divided by epsilon square. Just put this number in here. Then as n goes to infinity, then this goes to 0, this goes to 0, this goes to 0, then then this probability will go to 0. So again, you can show the Chebyshev inequality at the limit when n goes to infinity. So this result sort of tells you, even though you have some kind of short-range correlation, even if you have some short-range correlation, as long as the short-range correlation is short, now, okay, then you only have one additional term, and that term can vanish as you are making the n big. Now, what happens if you have a long-range correlation? Well, if you have a long-range correlation, then sorry, you wouldn't have the 0 here. You will have a lot of terms, and if the number of terms here is dependent on big N, let's say you keep half of those, then you cannot vanish this. You still have a big chunk of things to add, then you cannot show that it converges. So then, of course, you cannot prove the law of large number if you have a correlation, very strong correlation. Okay, so that also answers part B of this homework exercise. And I hope that those 3 problems, if you sit down and you work it out by yourself, you can appreciate more about the central limit theorem and also the law of large number. They're not that crazy, but if you really get through this thinking process, then you will really understand, oh, okay, a lot of numbers, convergence, why do we care about all these distributions in samples, what do they mean? So that would be very helpful as you are trying to understand more about this course. Okay, good. So that's all I have, and also I think that's about the time for this lecture. When we come back, we are going to talk about a new chapter. And this semester, I decided not to talk about random processes because to build the random process discussion, you need to spend a lot of time talking about the machineries. We spend so many weeks on PDF, PMF, and so on, and so it would take us a similar amount of time to just go through these machineries before we can talk about anything useful. So I decided to talk about another chapter. It's chapter 8. The course notes are already on the website. You can download it, you can print it out. It's called an estimation. The question is, now that I give you some training samples, how do you find out the model parameters? That could be useful, right? That could be very, very useful. Gaussian distribution, we know how to calculate mean and variance. What about Poisson? What about Bernoulli? What about a more complicated distribution? I have social networks. How do I estimate the underlying, the friendship relationship? What is the probability? So we want to talk about that, the estimation part of this course. Okay, so go back and then have a wonderful Thanksgiving break. Spend some time with your family, and then when we come back, we will finish the chapter on chapter 8. Okay, so I will see you after the break.